Stand still for a second and think about what is underneath you. Not the floor, not the street, not the dirt and rock a few feet down. Keep going. Drop past roots and pipes, past basements, past subway tunnels, past every mine humans have ever dug. Keep falling through hot stone for thousands of miles, and at the center of all of it sits something no human being will ever touch, a solid ball of metal, hidden inside the earth. It is mostly iron. It is roughly the size of the moon. It is about 3,200 miles beneath your feet. And for most of human history, nobody knew it was there. That hidden ball matters to you in ways that feel almost too large to belong to a normal day. The deep metallic engine of the planet is tied to the magnetic shield that turns dangerous particles away from Earth. It helps make a compass needle swing toward north. It belongs to the reason auroras shimmer at the ends of the world. But the person who first found clear evidence for the solid inner core did not have a probe or a camera or a tunnel through the planet. She had a desk. She had pencils. She had paper. And she had the patience to listen to the Earth when it rang. Her name was Inge Lehmann. In the 1930s, she was working in Copenhagen, reading the scratchy paper records of earthquakes from seismic stations scattered around the world. She was not standing at the center of a giant machine. She was one person at a table in a small country, sorting through traces by hand while the planet slowly gave itself away. Here is the mystery she noticed. When a large earthquake shakes the planet, the waves do not just travel across the surface, they move through the whole Earth. Some paths should be possible, some should be blocked or bent away. In one region, there should have been a kind of quiet gap, a shadow where certain waves were not expected to arrive. But a few waves were there anyway. Faint, annoying, easy to dismiss. To Lehmann, they were the clue. This is the story of how she followed that clue into the center of the planet without ever leaving the surface. And when we get there, when the board fills in and the Earth opens, you should remember where we began. One pair of feet on ordinary ground, with a hidden world glowing underneath. The first thing to get clear is that Earth is not one simple ball of rock. It is layered, more like an onion than a stone. The outer crust is the thin skin you live on. Beneath it, the mantle is hot rock, solid on short human timescales, but able to creep over geologic time. Deeper still is the outer core, a sea of liquid metal, and inside that, at the center, sits the solid inner core Lehmann helped reveal. The scale is hard to keep in your head. A mountain is tiny on this diagram. A drill hole barely scratches the skin. The center is so deep that even the fastest elevator you can imagine becomes useless as a mental picture. So for a long time, people were forced to ask a strange question. If you can never go there, how do you know what is there? One answer is magnetism. The moving, electrically conducting liquid outer core is a churning dynamo. It helps generate Earth's magnetic field. That field reaches far into space and bends charged particles away from the planet. It gives travelers a direction when a compass needle settles. It helps turn particles from the sun into curtains of light near the poles, but the magnetic field can tell you only so much. If you want to map the inside, you need the planet to send you a signal. That signal is an earthquake. Deep below the surface, rock breaks. The Earth rings like a struck bell. Waves spread through the interior, bending, slowing, speeding up, disappearing, and arriving at stations far away. Every station is like an ear pressed to the ground. This is the strange bargain of seismology. You do not get to choose where the earthquake happens. You do not get a clean lab experiment. You get a violent event somewhere on the planet, and then you get marks on paper. If you are patient enough, those marks become a map. Lehmann's work belongs to that bargain. She was reading the planet by listening to how it rang. The important thing is not that the waves were dramatic, it is that they were specific. A wave arriving a few minutes too early, or in the wrong part of the globe, can mean that the inside of Earth is not shaped the way you thought. A tiny blip can redraw a planet. Inge Lehmann was born in Copenhagen in 1888. As a child, she went to a progressive school where girls and boys were taught together, which mattered more than it sounds. She grew up with the habit of taking difficult work seriously, and she carried that habit into mathematics, geodesy, and then seismology. The world she entered was not built for women to move easily through it. Still, she became head of the seismology department at the Danish Geodetical Institute. That meant observatories, records, stations, correspondence, and a slow flood of earthquake data. The job was not glamorous. Much of it was careful reading. A seismograph is a beautiful machine because it turns invisible motion into a line. The ground moves, a drum turns, a needle draws. Somewhere far away, rock is broken, and here, hours or minutes later, the paper trembles with evidence. To most people, the record looks like a nervous scribble. To a seismologist, it is a sentence written by the Earth. Lehmann's gift was not theatrical, it was attention. She could sit with the records, compare arrival times, sort cards, and notice what should not be there. Denmark's stations, including stations linked to Greenland, were part of a wider listening network. But the network did not interpret itself. Someone still had to do the arithmetic. Picture the work without computers, columns of numbers, a pencil, a slide rule, the same question asked again and again under a late lamp. If the waves took this long to arrive here, what path did they take? That is where her story becomes almost stubbornly cinematic. Not because she is waving her arms in front of a crowd, but because the stakes are absurdly large. A woman at a desk is checking whether the map of the planet is wrong. And then, in the records, there is an odd little trace that refuses to behave. To understand the clue, you need two kinds of seismic waves. An earthquake begins with a rupture. From that rupture come several wave types. But the ones that matter most here are P waves and S waves. P waves are push waves. They squeeze and stretch material in the direction they travel. S waves are shear waves. They shake material side to side. That difference lets scientists read the inside of Earth. Waves spread in arcs through the planet. When they pass from one kind of material into another, they bend the way a straw looks bent in a glass of water. Inside Earth, the bending is not a trick of your eye. It is the wave changing speed as the material changes. Faster here, slower there. Curved paths through layers you cannot see. The liquid outer core creates a deeper clue. S waves cannot travel through liquid, so they stop at the outer core. P waves can cross it, but they bend strongly as they enter and leave. Stations around the world catch some waves clearly. Other regions fall into shadow. In the simple picture, that shadow should have stayed empty in a particular way. But on the paper records, Lehmann saw faint P-wave arrivals inside the problematic region. She circled the impossible arrival and refused to treat it as noise. The question was no longer, did the instrument make a mess? The question was bigger. What inside the Earth could send a wave into the shadow? This is where Lehmann's mind does the work. Suppose the core is not one simple liquid region. Suppose there is another boundary inside it. A P wave dives into the core, meets that deeper change, and bends again. Some of its energy can be redirected into the region that looked shadowed from the surface. That is the elegant part. The strange arrivals were not magic. They were messages from a more complicated interior. The path later known through P-prime waves made sense if the inner part of the core behaved differently from the liquid around it. There had to be a boundary. And beyond that boundary, the wave speed had to be different. In 1936, Lehmann published the paper with the small severe title. The title is almost comically modest for what it contains. It does not announce a revolution. It does not bang a drum. It takes bad fits and wrong guesses, and crosses them out one by one. Then it points toward a solid inner core nested inside the liquid outer core. Hold that image next to the moon. Hold it next to the depth below your shoes. She had not drilled. She had not photographed. She had not touched a sample, but she had found a structure at the heart of the planet by following waves through darkness. That is the quiet triumph of the story. The impossible waves were not impossible anymore. The fair version of this discovery matters. Lehmann was not the first person to realize Earth had a core. Richard Dixon Oldham had used seismic evidence to show a central core decades earlier. That was the first great opening of the deep Earth. Benno Gutenberg then sharpened the picture of the core boundary and the liquid outer core context. The outer core was already part of the story before Lehmann made her move. What she added was the inner core, not a replacement for the earlier work, a new layer inside it. This is how good science often looks when you slow it down. Not one person alone with all the answers, but a line of people handing the planet forward. Even then, a right idea does not instantly become the world's picture. There was skepticism. There were years of better records, better instruments, better calculations. Later observations converged on the inner core model and made the evidence stronger. The model was refined, because science does not stop at the first good answer. But there is still something sharp in the human shape of it. A woman who had done this work from the edge of the establishment could be respected and still not widely known. The major honors came late. Her name became attached to the boundary. She lived long enough to see the field change around her. The record stands because the reasoning stands. By the end of her long life, Lehmann had become one of the people you cannot remove from the map of Earth. Her life stretched across more than a century. The discontinuity she identified became part of how scientists talk about the planet's interior. The hidden core is part of the same deep system that helps shape the magnetic shield around the world. Every compass needle belongs to that larger story. Every aurora is a reminder that the inside of Earth is not separate from the sky above you. Modern seismology is vastly more powerful than the paper records Lehmann read. More people have entered the field who would once have been pushed to its edge. But the central lesson of her story has not gone out of date. You can learn something enormous from a small mark if you know what should have happened and you are honest about what happened instead. So come back to the ground under your feet. The planet feels still because you are moving with it. It feels solid because the crust is the only part you touch. But far below you, the Earth is layered, alive with pressure, heat, metal, and waves. At the center is the solid core. Put it beside the moon in your mind and let the scale sit there for a second. Inge Lehmann did not find it by seeing deeper than everyone else. She found it by looking longer at what everyone could have seen. That is a different kind of brilliance, and maybe a more useful one. Sometimes the world is not hiding because it is silent. Sometimes it is hiding because the signal is faint, and the first person to hear it is the one patient enough not to look away. If you want more night lectures like this, subscribe, leave a like, and tell me in the comments which hidden part of the planet you would want to visit if the trip were somehow possible.